Hello, it's Steve, and it is Geo-Rant time. I am currently driving through downtown Chicago, heading north. It is February 12th, 2017. The temperature is 50 degrees Fahrenheit, and the time is about 13:40. Yeah, this traffic is not cool, but I hope you're enjoying a warm winter, but that is not what this rant is about. Today, I want to talk about how we know what we know about geology, how we came to the idea that the earth is old and not young. And I'm not going to sit here and bash anyone's religion. I'm not going to do that. But the fact that religion insists, at least certain people in certain religions insist that the earth is young, I think this needs some explaining. First of all, I want to say it's not like in the 19th century, Darwin and a bunch of geologists, because there weren't geologists then, they were naturalists, got together and said, we're going to disprove the Bible. That's not what happened, okay? I just want to make that clear. I don't care what anyone tells you. You look at the history of how the science of geology evolved, and that did not happen, okay? That's a talking point people use who don't really have any evidence. Now, that being said, okay, that's all I'm going to say about that. I said my piece, okay? So, how do we know the earth is old and not young? Well, this has been a long process. Just like the forces that shape the earth have been a long process. Not as long as the forces that shape the earth, but still long compared to human lifespan. The science of modern geology didn't really get started until actually probably the early 20th century. The roots were laid basically in the late 18th and through 19th centuries. But as a science, it kind of got off to a late start. I mean, by the time we had radiometric dating to actually date undisturbed igneous rocks, Einstein had already come up with relativity. So physics was kind of way ahead of us. But it actually, the mid-19th century is when we started understanding things the way we do. We still didn't know how old the earth was. We had no idea. People guessed from a couple million to a few 100 million years, and they were all wrong. Of course, we didn't even know what powered the sun then. But during this time, people actually went out to look for evidence of the Great Flood. Okay, they didn't understand what geologic processes were forming the earth, so they went out looking for evidence of the Great Flood because they had the Bible. And what they found was evidence of great ice. They started finding evidence for ice ages. And the theory or the idea that ice could have extended from the mountains onto the continents and from the poles onto the continents was a fantastic idea. This is something we had not experienced before. We didn't know, and a lot of people were skeptical, and rightly so. And you should be skeptical of new theories, even if they fit well into the scientific picture, because if you don't, then you start accepting every willy-nilly crazy idea there is. And it's called skepticism. And I am still skeptical to this day about snowball Earth, the theory that the entire planet was frozen over at times in the Precambrian. I still have a strong problem with that. To me, the evidence is not there to sit there and say that actually happened. However, if the evidence does eventually present itself, I'll concede. Okay? Because that's how science changes and evolves. And even in the 21st century, we've had some crazy willy-nilly ideas that have been tested and nobody's found anything for. The one that stands out in my mind is this concept that the earth was shaped by magnetic forces, or the universe was shaped by magnetic forces, not gravitational. Well, it sounds like a cool theory, right? But people have been looking for evidence of this over the past 20 so years, and have found nothing. It's just like in the 19th century, the idea of the ether, they didn't find it, so you got to discard it. And I mean, some people are still clinging to that because that's their baby, but all evidence suggests that gravity is on a large scale is what influences the universe, not magnetism. Well, finally moving here. Okay, so now to get into it here. So how do we know what we know? Okay, so I already mentioned that in the 19th century, people started finding evidence of ice ages. But they still didn't understand. I mean, some observations had been made a long time ago. For example, the observation in undisturbed sedimentary rocks, flat sedimentary rocks, that the younger beds are on top of the older beds, and that bed is then younger than the one below it, and so on and so on. They knew that. They've known that for a long time. So people went out, and we really didn't understand volcanism. We didn't understand sedimentary processes. We had no clue. So people just started forming ideas together. And one popular one at the time was the idea that rocks precipitated from seawater. All rocks, all of them. Even granites, which we know now not to be true. You can't get a granite from seawater, but it was an idea because it's all they had. Some sediments are precipitated chemically from seawater, like some limestones, evaporites, those kinds of things, but granites, sandstones are not. Okay? And how do we know that granites are not precipitated from seawater? Well, we can melt rocks in labs. This is not beyond our capability. All of geology isn't just looking at rocks and going, ooh, ah. That's not it at all. As a matter of fact, the melting of rocks and watching what minerals form is how we got Bones reaction series. So there is some experimental part to geology, but most of the experimental part is related to geophysics or geochemistry. I am neither of those. I am a stratigrapher. So I am one of those guys that goes out, but I go out, look at the rocks and go, ooh, ah. Sorry about that. Let me extinguish this. Okay. All right. Okay. So back to it. So we went out looking for evidence of a great flood, and we found an old Earth. Okay. And then in the early 20th century, radiometric dating came about, and that is a strong proven science. No one has ever disproved it. There are things that will mess with radiometric dating, and we are aware of these things. Such as, like, if you want to find the age a rock was deposited, you really need undisturbed igneous rocks. I mean by undisturbed igneous rocks, I mean either magmas or lavas that have hardened and haven't subsequently been folded or bended or any of that stuff, because that can mess with the dating. And we have an ample supply of those on the planet throughout the geologic record. This is why dating metamorphic rocks is difficult, because a metamorphic rock is a rock that has been highly deformed under heat and pressure, but not to the melting point. And that could mess with the radiometric dating, and we are aware of this. Sedimentary rocks pose another problem. The most common mineral taken from a rock to date it is called a zircon. And zircons are very reliable, they're very durable, they're very resistant to weathering. And in a sedimentary rock, if you pull a bunch of zircons, sedimentary rocks are formed from the weathering of pre-existing rocks, or this, I'm excluding carbonates here, like limestones. I'm talking about clastic rocks, okay? They're formed from the weathering of other rocks. So even if you pull a zircon from a sandstone and say you get an age, it doesn't matter what that age is, that is not the age that sandstone was deposited. That is the age that original zircon from its original source rock, probably a granite or something like that, was solidified out of a magma chamber. Okay, so when you use zircons to date sedimentary rocks, we don't really do this in the Phanerozoic because we have fossils. We can do biostratigraphy, but Precambrian rocks we don't have that. So we will often pull zircons from things like sandstones. So if I pull a bunch of zircons from a sandstone and I get a bunch of dates that are around 1.3 billion years, and then 1 billion years, and then 900 million years, I have to assume that sandstone was deposited at or younger than 900 million years. You cannot be older than your youngest zircon, okay? So that, I just wanted to explain as quickly as I could why we even bother dating rocks, okay? So radiometric dating in the early 20th century started pointing to an early Earth, or to an old Earth that formed early in the solar system. And then we had things like, when we went to the moon, we got moon rocks, and we could date those because the moon has no sedimentary rocks. They're all igneous rocks. So, so now we had, so over a course of about 100 years, and it took 100 years to figure this out, we started observing rock units, and we could physically date rock units. And what we learned is that the geologic processes happening today, especially with sedimentary rocks, have been going on for billions and billions of years. We can take modern analogs and find them in the rock record. On the eastern coast of the United States, we have a passive continental margin, and we see certain deposits, sandstones, shales, stuff like that. And we see that exact same sequence in 2.5 billion year old rocks around Lake Superior, okay? So these processes have been going on for a long time. And the Earth still makes every type of rock that it always has. There's one exception to this, and that's a Geo-Rant for another time. And the Earth does not any longer make banded iron formation, which is a sedimentary rock. That is the only one Earth no longer makes, okay? And there's reasons for that, but like I said, that's a rant for a different time, okay? So now don't get me wrong, there are catastrophes. Catastrophes do happen. Asteroids do impact, volcanoes do erupt in huge amounts. Things like that happen, but they're sporadic, and they're within the geologic time frame. I mean, you're dealing with millions and billions of years. Those events are that they're nothing. They're blinks of an eye. They don't last forever, okay? We like to focus on those because asteroids killing the dinosaurs is kind of cool sounding. But in reality, most of the Earth is, over long periods of time, it's very dynamic. Within our lifespan, or even 5 lifespans, or even 10 human lifespans, consecutive lifespans, the processes are not observed readily. Some processes are, but most are not, okay? So we went and we just started looking through the rock record. We went out and we started looking at sediments, and we went out and started dating things. And it just quickly occurred to us that the Earth is old. It can't be young. It just can't be. And every time someone has, in a testable, reproducible, predictive manner, tried to disprove an old Earth, they have come up with nothing. Okay? It has stood the test of time. And for some reason, say, beyond a shadow of a doubt, someone did prove, it's not going to happen, but they did prove that the Earth was young, I would have to concede, okay? But no one has ever proved that. All the evidence, all of it, not a tiny bit, but all evidence, and I say evidence, I mean actual testable, reproducible evidence. I'm not talking about, well, I had this thought, so I'm going to use that as evidence, okay? Every bit of evidence points to the Earth being old, and very old, okay? So, I guess that's it. I'll stop right there. I'm about to get off on my exit here. But I hope you learned something.